Hi folks, welcome back to Math with Captain Rod. The purpose of this video here is to just conceptually describe a quantity called motional EMF or induced voltage. So let's take a look at this picture here. So what I got a picture of is a bar magnet, and I tried to at least sketch the field line configuration around it. Bar magnet configurations tend to look a lot like this. And again, that field configuration has a special name. It's called a magnetic dipole. This is not the best drawing of a dipole field I've ever drawn, but it's good enough for this picture. And what we're going to talk about now is what happens to maybe a conductor if I move it through this magnetic field. So we're going to imagine that we're moving the conductor in this direction. Now, very important to realize why that way. All right, so if I move it this way, there's not a lot of activity going on. Let me explain why. So the magnetic force, remember, on charged particles is given by QV cross B, which is equal to QVB sine theta, where theta is the angle between the velocity and the magnetic field. So if this particle here at the instant shown is moving to the right, then the velocity vector is basically tangent to the magnetic field vector, and the angle between them is basically zero for all particles here inside of this guy. So there's really no net magnetic force, or not. The magnetic interaction is not real substantial, right? However, if the velocity vector points this way, so meaning that this is moving through this magnetic field at a right angle, well, now something much more interesting happens. The conductor, remember, is, well, all material is made up of protons, neutrons, and electrons. And all of the protons will experience a magnetic force, a QVB force, and the direction here, let's see, is defined by the cross product. Now, this is kind of hard to describe in this screen here. I've got other videos that are more three-dimensional for doing right-hand rule, but any positive charge carrier is going to feel a force in the minus k direction. So hopefully you've seen, I'll just put an F, it's going to be in the minus k, or into the page. What I do when I talk in class and when I make my videos, unless otherwise stated, I always use what I call a Zakia coordinate system, x, y, z at you. So hopefully you've seen my videos on right-hand rule. If you take the velocity vector, which is this way, and the magnetic field vector is this way, and you cross them with your right hand, putting your fingers in the direction of V, sweep towards B, your thumb will be pointing into the page. So any sort of magnetic force on a positively charged particle is going to be in the minus k direction. Now, any electrons will have exactly the opposite of that. The electrons will be forced in the plus k direction. Now, the protons are not free to move, but the electrons are, at least some of them, the outer shell electrons. If this is a conducting material, then the outer shell electrons are free to move. So if I kind of take a look at this now, kind of from a side view here, what are we going to see? Let me just kind of looking here. So, and again, this is going to be a little bit harder to tell what's going on here. If we're looking from this viewpoint, in this picture, we're going to now have electrons along here. Well, I'll just say we're going to get a charge shift is the appropriate thing to say, such that we have electrons here, or a net negative charge on the right, and net positive charge on the left. And that's because the electrons have felt a force in the plus k direction. In this picture, this is plus k. And then this way is plus j, and at you is now plus, actually I is actually away from you in this picture. All right, so looking from this viewpoint here, as this conductor moves through this magnetic field, we're going to get a charge configuration that's going to look something like this. So now what's going to happen is we're going to get an electric field now inside of the conductor. And it's going to point this way. Now at this point, hopefully you're going, wait a minute, Captain Rod. I thought that there weren't any electric fields inside a conductor. If you think back, hopefully you've seen my videos on the what I call the IFACTs, important facts about conductors. And one of them is no field in the conductor. Well, if you listen carefully, hopefully somewhere in that video, I put a little qualifier in there. That was assuming a static problem. This is not static. This conductor is moving through a magnetic field. That will make charge shift in the conductor. And when you have the charge shift, you now have an electric field in the conductor itself. Now, you also now have a potential difference from one side to the other. Because remember, potential difference is field strength times distance. Potential difference is measured in volts. Right. This potential difference is caused by the motion or the velocity of this conductor in the magnetic field. And for that reason, it's called a motional EMF. Right? So I think what I'll do here is draw some other videos, or I'm sorry, I think I'll pause this, redraw the picture, and look at some more examples of motional EMF and focus on what side's going to be at the higher potential and whatnot. So give me a moment here to clean this up, and we'll be back and chat more. All right, I'm back. So what we're going to do now is we're going to talk about the effects of this conductor as it moves through a magnetic field that's very uniform. So I drew, just kind of 9 vector symbols here to kind of represent this. The field we're going to imagine is in the -k direction or into the page. And again, for this video, anybody watching this, the intention here is that this magnetic field is uniform anywhere in the picture. So, it applies here, here, here. I just don't want to draw them all, but in this entire region in space here. And what we're going to do is we're going to look at the effect on this conductor here moving through the field in different directions. So let's draw the velocity vector in green. Actually, no, we'll draw the velocity vector in black. So imagine now that this conductor is moving through the field this direction. So there's my velocity vector. Now, when you're dealing with charged or conductors, it is the electrons that are free to move. And typically, when you're talking about metals, the most typical example is outer shell electrons moving through the conductor. So, yeah. But you are pretty much free to imagine any charge carrier you want. So I'm going to focus on positive charge carriers here, because it doesn't really matter if you focus on pluses or minuses. You'll end up with exactly the same thing. So if you imagine a positive charge carrier somewhere in this conductor, and remember that the magnetic field is in the -k direction, every positive charge carrier is going to feel a force given by V cross B. Now, it's kind of difficult on this page to demonstrate right-hand rule. If you're not familiar with right-hand rule, go back and watch my videos or maybe somebody else's videos on how to apply the right-hand rule. But anytime you do right-hand rule stuff or cross-product stuff, you're going to be using right-hand rules. And you always put your fingers parallel to the first vector. So if you're watching this, take your right hand, put your fingers exactly parallel to this screen. Not close, all right? When I always recommend in class, you should be able to use your fingers as a straight edge to draw that vector. Then rotate until you can sweep towards the magnetic field vectors. If you are following this video, your fingers should be straight up right now, and your palm should be basically into the screen. Like you should be able to lower your hand and actually touch the screen. Sweep, and you should be concluding that the magnetic force on that charged particle is to the left. All right. Now that means that on this conductor, we're going to get a charge configuration that's going to look like this: pluses on one side, minuses on the other. And that means we're now going to have a potential difference here across this. And the left-hand side is now at the higher potential. Now, I'm going to save the calculating the potential difference for another video. This video is just intended to be conceptual in nature. So, now we're going to talk about, different velocity vectors. All right, well, what if our velocity vector was pointing to the left? Oops. What's going to occur now? So there is our velocity vector. Meaning that this object is now moving left. All right. So now we're going to, again, look at force directions. And my advice, just imagine a positively charged particle, within this conductor, a nucleus. And now, to do the right-hand rule, if you're watching this video, put your fingers, take your right hand, make the fingers nice and straight, make them parallel to this velocity vector. They should be pointing from your right to left. Now you're going to rotate your hand so that you can sweep towards the magnetic field vector. You should be rotating your hand until your palm is facing the screen again. And then sweep towards B means like close your fingers towards B. Your thumb should be pointing down. So the magnetic force on any charged particle, any positively charged particle, should be down, which is in the -j direction in what I call a Zakia coordinate system. That means that the charge configuration on this conductor, charge will shift so that we have a pluses on the bottom and minuses on the surface, because every positive charge in this conductor is going to feel that magnetic force down. Now they're not free to move. That's okay, because every electron, or all the negative charge in the conductor, is going to feel a force up in the +j direction. And what that's going to do is give us an electron shift vertically. That's going to leave us with kind of a gap here where there used to be electrons, now they're not. That's now a positively charged region, and that's going to give us extra electrons here. And again, it's not that an electron gets all the way from here to here. It's just that every electron in this conductor is going to feel a force in the +j direction. Some of them are free to move, and there will be kind of a shifting that takes place. All right, now we're going to have an electric field in the conductor, and that electric field is going to point this way. Oops, I use a different color for that. I use red. So now we have electric field vectors that point this way in the conductor. Remember that electric fields always point away from positive charges and towards negative charges. So there's our electric field vectors. And now we have a potential difference between the bottom of the conductor and the top. Right? Remember that, I'll just write this in a kind of an algebra sense. Potential difference is field strength times distance. Now, see how we have a field and a vertical distance here. I'll make another video about calculating these potential differences. For now, I'll just say this. This electric field here, this is going to depend on how fast we're moving it through the field, right? And so the potential difference is going to depend on speed, no doubt. It's also going to end up depending on the magnetic field, right? And it's going to depend on this distance here, because the further the distance, the stronger the field. So again, this is an example of what's called a motional EMF. Most physics people like myself, we don't like the term EMF, but anyway, EMF is just a kind of a poorly chosen word for voltage. It's a voltage that occurs because of situations like this. In this example, the bottom of the conductor is at the higher potential. I always like to talk about. I think it's very useful to know which sides at the higher and which sides are at the lower potential. So yeah, this video is at 13 minutes 40 some seconds. I think we'll call that good enough. Hopefully, it has at least conceptually described why you can get a potential difference in a conductor when you move it through a magnetic field. Everybody have a great day.